I'm Tony Hansen, the original developer of the Aethalometer for the real-time measurement of aerosol black carbon. 40 years ago, I started my career as a postdoc studying the effects of these particles. When sucked through a white filter, the deposit of particles creates a black spot. And we realized that this black spot must represent the presence of carbon particles in the atmosphere. As a young man, I showed this black spot to a very senior scientist who said to me, "That's not important, it's not in our atmosphere, you're wasting your time." Well, now, 40 years later, it turns out that black carbon is the #2 contributor to global climate change and the #1 indicator of the health effects of exhaust emissions on people. So black carbon is very important. And if it's important, we have to be able to measure it, because if we can't measure it, how can we control it? Here's a sample that is just the edge of a sheet, and in the center of the sheet, the black deposit is a deposit of exhaust particles from buses and trucks near a busy roadway. The label of this filter shows the date, 1978. Even after almost 40 years, that black material has not disappeared, it hasn't oxidized, it has not evaporated. Black carbon is a persistent pollutant. That's my handwriting on the label, and when I collected this sample, my hair was the color of the center of the sample, not the color of the edge. But the fact that it's so black and so permanent is why black carbon is important in the atmosphere. Black carbon is now known to be responsible for a wide range of health problems. Exposure to vehicle exhaust leads to all kinds of respiratory, cardiac problems, even problems with memory and cognition, reduced lung function in children, and every other imaginable physiological problem. And this is the reason why black carbon is one of the pollutants whose measurement is important for maintaining air quality in cities and in our countryside. For climate change, we find that the presence of highly absorbing black material in the air absorbs sunshine, changes the albedo of the planet when seen from space, and strongly absorbs light and energy if the black material is deposited onto snow and ice. The Arctic is melting. The Himalayas are melting. Part of the reason for that melting is that black material is deposited onto the snow and the ice, and when the sun shines on it, the energy is absorbed and the snow and the ice melts. Finally, particles in the atmosphere affect the formation of precipitation and rain. And if the air is filled with particles, which would include black carbon particles from vehicle exhaust and from combustion, then we have found that the rainfall is affected, reduced, or changed in its nature. And indeed, one of the concerns of the government of India is that the monsoon patterns are changing, the patterns of rainfall are changing in India and China, and some of that can be attributed to the particles in the atmosphere. In 1979, I realized that if I took an original white filter and shone light through it, and if I then watched it for several hours while I was sucking air through the center of that filter would gradually become grayer and darker, proportional to the concentration of black material in the air. And that if I was shining light through the filter, that light would gradually get less and less over time. And that if I could measure the rate at which the light intensity was decreasing, I would be measuring the rate at which the black material was accumulating, and that in turn would be directly proportional to the concentration of black material in the air. And that if I could suck air through a filter and shine light through it at the same time, I could get a real-time measure of the concentration of black carbon in the air. That was in 1979 that the concept was first invented. We had to give the instrument a suitable name. In the classical Greek theatre from 2,500 years ago, the characters wore either white robes or black robes to signify their role in the drama. And the people wearing black robes would blacken their clothes with soot. And the classical Greek word for soot is eth, and there was a verb, ethalum, meaning to blacken with soot. And so clearly, this was the correct name for the instrument, the aethalometer, to blacken with soot. And this instrument performs the measurement in real time. We did our first ever measurements in 1980, and at that time it was revolutionary because there was no other instrument that could measure aerosol optical properties in real time. This is the first aethalometer that I made when I formed the business Magee Scientific for the purpose of commercializing the technology which I had developed in the university laboratory. And in this instrument, there was a light bulb up here. The air would pass through a round filter, a circular filter, and get sucked out the back by a pump. And as that spot gradually became darker and darker, the intensity of light would diminish and we would measure that. This was an extremely crude prototype, but when we made it, it was the first instrument in the world that could measure the optical properties of suspended particles in real time. This is another one of the early instruments. This one dates to 1990, and this one was actually used on board a research ship that sailed across the Pacific, measuring the amount of smoke that was coming off of the mainland of China and transporting across the Pacific Ocean all the way to the United States. As you can see, the technology's improved a little bit more. I have digital readouts on the front panel, and the optical chamber now shows more clearly how it works. The light source is at the top, the light shines through, the circular filter is here, the air is sucked in at the back and out through the pump. As the spot becomes darker and darker, the optical intensities get smaller and smaller, and this was connected to a very early model of computer that would record the numbers and perform the calculations. And in this way, this was really the first commercially usable version of the aethalometer from about 28 years ago. After many years of continuous technical improvement, this is the latest model of aethalometer, which is now made at our partner company Aerosol in Slovenia in Europe. Instead of a single filter that has to be changed by hand, we have a roll of filter tape. And you can see the spots on the tape representing the deposit of particles. The air is drawn through by an internal pump. The spot gradually becomes darker and darker, and when the spot reaches a certain limiting threshold, the instrument will pause, move the tape forwards, and then start over. In this way, we have continuous operation that can last unattended for weeks or months, depending on the amount of material in the air. The roll of tape feeds from the left to the right, and one roll of tape will last many weeks in a polluted location, several months in a clean location, and there's one of these at the South Pole. At the South Pole, the air is incredibly clean, but nevertheless, we can measure a tiny amount of black carbon that has circulated all around the world and finally ended up at the South Pole. There, the instrument took 1 year before it made one spot. The instrument data is presented on the screen, a touch screen, which provides all of the interface for the user to control the functions and observe the measurement. In normal use, of course, we don't look at it because it's running automatically. But when the operator comes to it, the screen will show the status of the instrument, the measurement, and allow you to control the functions. What is one of the more important recent developments is that we don't just analyze at a single wavelength of light like the earliest instruments which used a bulb. Here, the light source is an array of LEDs, but we have 7 different colors, 7 different wavelengths, ranging from the infrared to the ultraviolet. Because we have found that the absorption of light by particles can be influenced by the composition of the particles, especially the presence of biomass smoke, which means smoke from burning wood, cigarette smoke, coal smoke, materials that have an aromatic component to them. If you can smell the smoke, your nose is smelling those aromatic components, and those compounds have an increased optical absorption at shorter wavelengths. In other words, purely black diesel smoke absorbs the same across the entire spectrum. That's why it looks black. But smoke from biomass burning, from wood burning, for example, will show increased optical absorption at the shorter wavelengths. By analyzing at multiple wavelengths which are contained in the optical source, and by comparing the data between the different wavelengths, we can automatically calculate the amount of material that appears to have come from biomass burning. And indeed, the mathematics in the instrument can display that on the front panel so that the user or the air quality manager will know how much of their air quality problem is coming from diesels and how much of their air quality problem is coming from biomass burning. There are a number of accessories which are offered along with the aethalometer that help to improve its data, calibrate it, validate it, and make it sample the particles correctly. This is the neutral density optical kit. This is a kit of optical filters, filter glass elements of calibrated and known optical density. When these are inserted into the optics of the instrument, an automatic calibration validation routine is performed, and the results of that reassure the operator that the instrument is performing exactly the same as it did when it was manufactured. When manufactured here at Aerosol, every instrument is calibrated against standards which can be traced back to the National Institute of Standards in the USA, NIST traceability. So the original calibration when the instrument is manufactured is NIST traceable, and the use of the neutral density optics kit allows the operator in the field to validate that performance and be assured that the instrument is working correctly. This can be done without taking the instrument out of service. The process only takes a few minutes, and it's a routine quality control, quality assurance process that is recommended for routine use of the instrument. So the neutral density kit allows you to trace the calibration and your data back to NIST standards. We also offer a sample stream dryer. In very humid environments, such as the south of the USA, some parts of India, South China, any tropical location, the aerosol, the outdoor air, can be extremely humid, and when brought into an air-conditioned room, this can cause problems with the instrument. Also, the GAW has recommended that all aerosol properties should be measured at a relative humidity of 40%. The dryer has a diffusion membrane which is semi-permeable only to water vapor molecules, which removes the water vapor from the sample stream and reduces the dew point, the condensation temperature, to below 0 degrees C. This ensures that the humidity is low enough that humidity will never be a problem in the instrument or a problem for accurate scientific data. We also normally recommend the use of a size-selective inlet, such as a PM 2.5 cyclone, which will only pass particles smaller than 2.5 microns and which will exclude large mineral dust such as wind-blown dust, etc. And we also offer a meteorological sensor so that the ambient temperature, pressure, and relative humidity can be recorded in the same data file in the instrument. So all of these taken together create an ensemble of equipment to provide accurate data that can be checked for QC, QA, and traced back to original standards. This is essential for routine air quality monitoring operations where long-term traceability and trend analysis is necessary to know whether or not the policies that are put in place by the local authorities, by the government, are having the desired effect in terms of quantitatively reducing the concentration of black carbon in the air. Examples of these policies could be, for example, to reduce or limit the access of vehicles to the center of a city, or for a municipality to change all of its buses from old diesel buses to new diesel buses or new electric buses. These policies are put in place to try and improve the air quality in the city and to reduce the risk to the health of the population. However, in order to know whether these policies are effective, we have to have continuous, accurate data. And that is what the Aethalometer, together with these accessories, can offer, is a continuous, accurate data whose accuracy can be traced back and which can be related to measurements that may have been made 1 year ago, 5 years ago, or 35 years ago. In this way, we can determine whether or not the policies which we have put in place are having the desired effect relative to the amount of money that is being spent on those actions. In 1978, I started this work. I was sure that black carbon was important. 40 years later, this is the result of that commitment. We stand by this 100%, and we value your input, and we thank you very much for your interest in environmental science and black carbon in particular. Thank you.